Hi, this is Munyebin at PostTech. I'm excited to present our work, TextMania, Enriching Visual Features by Text-Driven Manifold Augmentation. This is joint work with Jisoo Kim, Hongyup Kim, Dr. Giroson, and Professor Tae-Hyun. In this work, we propose a new data augmentation, TextMania. Uniquely, it directly augments the visual feature by utilizing text attributes. Our method has some interesting features. First, TextMania is an intra-class semantic perturbation. We densify all the samples, so it is especially effective for densifying sparse class samples. Second, we use attribute information, such as color or size. This information is extracted in the text embedding space by simple subtraction. For example, the red attribute is extracted by red bool minus bool, and we call it a difference vector. Last but not least, we transfer the difference vector from the text embedding space to the visual feature space. It is based on the finding that general language models such as BERT and GPT can understand visual semantic information, at least effective for augmenting visual features, even they have not been exposed to visual information. Before applying TextMania, we skim the naive model training process. When the image and the corresponding label are given, we feed the image to the encoder to obtain the image feature, and measure the task loss with the given label and train the model. For TextMania, we augment the image feature by injecting perturbation. And this perturbation is from the text attributes. This is the detailed training process with our TextMania. First, the image and the corresponding label is given as usual. We synthesize the text variant by adding the attribute text. Then, we extract the text embedding from the pre-trained language model and compute the difference vector. We project this difference vector with a simple linear layer and use it as a perturbation on the image feature. Finally, the target task model is trained with the augmented feature. From this section, I'll present the characteristics of difference vector. First, we compare our difference vector and the random vector as a strong counterpart in the sense of sample densification. The results show that the accuracy of difference vector is higher than random vector, although both vectors densify sparse samples, which demonstrate that the semantic information is important. Because, as shown in the image manipulation results, difference vector embeds semantic attribute information, but the random vector is not. Next, we compare our difference vector with the direct text embedding, which is from a single attribute red. Both contain semantic information red, but the accuracy of the difference vector is much higher than the direct one. This demonstrates that the remaining contextual meaning is important. In other words, the red from the difference vector contains the role of modifying bool in a sentence, while the red from the direct one contains just the noun red. This is also shown in the TSNE plot. The direct text embedding for the attribute yellow is represented as a single point, but the difference vectors for yellow from different classes are represented as clustered multiple points. We think that this slight difference in the cluster is rooted from the remaining contextual information. Experimental results in the long-tailed recognition and scarce data classification demonstrate the effectiveness of our TextMania. In both cases, TextMania achieves better accuracy than mixed-based methods. Surprisingly, the text model brings improvement to visual classification tasks, although they have not been exposed to images. And when we use the mixed-based method and our TextMania together in an evenly distributed case, it brings a synergy effect. This is because they handle different levels of perturbation. The mixed-based method is an inter-class perturbation, and our TextMania is an intra-class perturbation. We will conclude this presentation with our findings and interesting points. First, although the language models are trained without visual information, the text embeddings have visual semantic information. Second, this information can be used for visual semantic augmentation by aligning to the visual domain with a simple linear projection. Finally, the direct embedding and the difference vector exhibit low similarity because they contain different contextual information. If you want more details, please visit our project page or our poster session. Thank you for listening.